Hello and welcome. This looks like a complicated problem. In this problem, there are two tanks. One contains purely hydrogen, one purely CO2, and they're allowed to partially mix so that finally we have hydrogen and CO2 in both tanks, but on the left tank we have a mass fraction of 0.5 for hydrogen. We don't know what is the mass fraction of hydrogen on the right tank. They're not necessarily in the same composition. Also, the conditions are initially well supplied, and the tank loses heat, and finally the temperature becomes 25 degrees Celsius. Initially, as you can see, the left tank has a temperature of 20 degrees, right tank has a temperature of 100 degrees Celsius. So there is heat transfer, and then there is mass transfer involved in this problem. We are supposed to find what is the final pressure in each tank and how much heat has been lost and what is the entropy generation. So obviously we're going to use, in this particular case, a binary mixture because constant specific heat assumption means we are going to use PG model. And of course, this is a case of, a semi-mixing problem, not a full mixing problem. But a few things, generally in a binary mixture, the part A, you will notice that in the TESTapp, we'll have a variable called XA. Component A in this case is hydrogen. So for state 1, which is the left tank's initial state, we can say XA equals 1. And for state 2, XA equals 0. Basically, if we set up a mixture of hydrogen and CO2 to obtain a pure component, we set mass fraction to be either 1 or 0, then it becomes purely hydrogen, purely CO2. For the final states, XA or hydrogen mass fraction is given to us as 0.5 right here. So we can calculate the hydrogen mass fraction for part B or state 4 by using the logic how much hydrogen really escaped from tank A. How do we do that? The original mass of hydrogen on tank A, part A, was M1, state 1, mass at state 1, pure hydrogen, minus how much left? The mass of hydrogen in tank 3, in tank A at state 3 is M3 times XA at state 3. So this is the total mass of hydrogen that left tank A. Therefore, this must have entered tank B, which originally had 0 hydrogen, and divided by the mass of, state 4 will give us the mass fraction. So this is, I guess, the main equation that is, needed to solve the problem correctly. Okay, so let's launch a suitable TESTapp. We go to the TESTapp page, and obviously it's a closed system, so you follow the generic route and simple process, non-mixing process, which is totally, that there is no exchange between masses in non-mixing process, but we have a semi-mixing process. Mixing process, on the other hand, is completely mixed. In other words, at the end of the mixing process, we'll have exactly the same mass fraction of hydrogen in both tanks. So we choose the semi-mixing process, PG plus PG model, and that brings up to the app. Fluid A is, of course, is hydrogen. We already told that. And fluid B is CO2. So let's now evaluate the initial state. Initial state has state 1 is pure hydrogen, so XA equals 1. And the conditions given are 200 kPa and 20 degrees Celsius. And finally, the volume is 10 meter cube. So state 1 is fully evaluated. Now let's go find state 2, which is pure CO2. So XA equal be 0. That's the thing about binary mixture. A pure gas is made up by setting mass fraction either 1 or 0. Then what else we know about state 2? 600 kPa is the pressure, and temperature is given as 100 degrees Celsius. And the volume is 3 meter cube. So pure carbon dioxide has been calculated, the state of pure CO2. For state 3, which is our left tank, we have a hydrogen mass fraction of 0.5, which is the default anyways. The temperature is given to us as 25 degrees Celsius because that's the surrounding temperature, the final temperature. And of course, tank 3's volume is the same as volume of tank 1. What else is needed? We also, mass is given to us. So at that point, the mass is 3 kilogram in the left tank. So therefore, state 3 is completely evaluated. For state 4, we don't know. First of all, let's put the obvious thing. Volume must be equals volume at 2, and mass must be equals M1 plus M2. That is the total mass to begin with, minus we have already evaluated M3. So that should give us mass and volume of tank 3. Of course, we don't know the mass fraction. That's the most important thing to find. Oh, we also know the temperature equals T3. Obviously, this information is not enough to find the state because mass fraction or mole fraction, the composition is needed. So how much is that? The equation that we developed, let's just enter it here. It should be equals M1 minus M3 times X underscore A of state 3, parenthesis, divided by M4. So that should evaluate the state. To check the equation, you can put the pointer over and take a look at this location. In other words, always remember that when you put the pointer over, more information is supplied. When you put the pointer over X, any variable, you can see that the formula as well as the value is displayed there. So now we already found the pressure of both the tanks. Let's go and find the heat transfer and entropy generation. To do so, notice that already the system is shown here. Because we have selected semi-mixing, we can see that there are two components, BA state and BB state. So we load state 1, pure hydrogen. Notice it's populated as pure hydrogen. And state 2, pure CO2. Final state, we have state 3 and state 4, and they're both hydrogen plus CO2. We know that there is no boundary work because the volume never changed. Oh, and the boundary temperature is 298 Kelvin, or is given 25 degrees. Let's enter 25 degrees Celsius, which is actually 298 Kelvin anyway, the default value. So now you can see that once we press calculate, both the heat transfer and the entropy generation is calculated. So using binary mixture is the only trick is that you have to somehow figure out the mass fraction or mole fraction of each component. Mole fraction of component A, and then everything else is like any other thermodynamic model.